So, we continue our discussions with space vector PWM. So far we have seen what is a space vector, and space vectors can also be realized using the graphical way, and we have seen the space vector of the pole voltage, and from which we can derive the space vector of the phase voltages. And these are the space vectors for, there are 8 space vectors for the converter, 3 phase 2 level converter. There are 8 space vectors as you can see on this slide, and these 8 space vectors are denoted by these red colored dots, and there are 6 such vectors, and there are 2 vectors here at the central position, and because they are vectors, they are indicated by arrows. Okay. So, in this diagram there are altogether 6 active vectors which are at the corners of an imaginary hexagon, and there are 2 zero vectors which are situated at the center of this hexagon. The magnitude of these vectors are all same, that is why it is a regular hexagon. So, the magnitude is 2/3 Vd, and the 6 sides they are making an angle of 60 degree. The switching state, we have so far denoted the switching states by 100 or 110 or 010. An alternative way of denoting the switching states is plus minus minus or plus plus minus, minus plus minus, like that. Here this plus minus minus corresponds to like 1 representing plus and 0 representing minus, and here also 0 representing minus. So, this is an alternative way of representing the space vector diagram switching states. There are of course minus 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 and plus 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 corresponding to 0 0 0 and 1 1 1. These are producing the 0 vectors. So, these 8 space vectors are basically forming the boundary of an imaginary hexagon, okay, which is shown by the dotted line in this figure. The hexagon is imaginary. So, there are in this diagram there are only 8 vectors, but for the sake of understanding and for the sake of easy implementation of space vector PWM, we can think of the boundary as an hexagon. Of course, this is imaginary. So, once we have made this boundary, once we have drawn this boundary, we can now divide the whole hexagon into 6 sectors. Okay. These sectors are 1, 2, 3, 4, 5, 6 as you can see in this diagram. The sectors are triangular in nature. The reference vector at any point here can be realized by switching the 3 nearest vectors in the same sector where the reference vector lies. Okay. This we have seen. Now, what is the maximum voltage? The maximum voltage can be obtained by observing the space vector diagram and the resultant vector which is inside this space vector diagram. So, you can see here we have seen that the resultant space vector is a vector which is rotating. For example, this is a resultant vector here and it is rotating. So, what is the length or what is the maximum length of this resultant vector? The maximum length of the resultant vector or the reference vector is obtained when this resultant vector corresponds to the maximum or the biggest circle which can be inscribed inside the hexagon. This blue colored circle is the biggest circle that can be inscribed inside the hexagon. So, what is its magnitude? The magnitude can be easily obtained by observing that the side of the hexagon is equal to 2/3 VD, and this triangle here, in this triangle, say I give the name OAB. In this triangle OAB, the angle AOB is pi by 6. Okay. So, therefore, the length of the side OA is equal to OB into cos 30 degree. That means, it is equal to 2/3 VD into cos 30 degree, which is shown here 2/3 VD into cos pi by 6, which is equal to 0.577 VD. So, the length of the vector VR max is equal to 0.577 VD, where the length of the vector V1 equal to the vector OB is equal to 2/3 VD. So, the maximum voltage that can be obtained in space vector PWM is equal to 0.577 VD. We can compare this with the Sine PWM technique, and in Sine PWM technique we found out that the peak AC voltage that could have been obtained was 0.5 VD, where the sine wave was touching the height of the carrier. As soon as the sine wave was touching the height of the carrier, we say that we are reaching the end of the linear modulation, and that magnitude was 0.5 VD, because the sine wave can touch up to VD by 2 to minus VD by 2. So, it was 0.5 VD or VD by 2. So, compared to that, the space vector PWM gives us 0.577 VD. Okay. This is the maximum voltage we can get, and that can be impressed on the load. So, load peak phase voltage is 0.577 VD, and this is about 15% more than what can be obtained with Sine PWM. So, Sine PWM we obtained 0.5 VD, and in space vector we have obtained 0.577 VD. So, which means we are obtaining 15% more in space vector PWM from the same DC bus voltage. So, this is the advantage of using space vector PWM. Okay. And we have earlier seen that by introduction of the third harmonic, we can also get 15% more, and in space vector also we get 15% more. So, from the point of view of DC bus utilization, both the third harmonic addition and the space vector PWM are same. They give the same DC bus utilization. However, the harmonic performance of space vector PWM is better. People generally prefer the space vector PWM. Now, as you may have realized that although space vector PWM gives us 15% more utilization as compared to sine wave, but it involves substantial calculation. For example, we have to first identify where is the reference vector, whether it is lying in sector 1, sector 2, sector 3, etc. Then corresponding to that sector, we must have a table, a kind of a lookup table or something similar to that, where we can say that okay, in this sector these are the 3 nearest vectors, and then we have to make the timing calculations, the formula that we have seen T1, T2 and T0, we have to calculate those formulas, and then we have to do the actual switching on the converters. So, the space vector PWM technique which we have discussed so far involves substantial calculation, but initially the space vector PWM, when it was implemented, was done in this fashion only, which involved a lot of calculation. But later it was realized that it can also be done using carriers, like what we do in Sine PWM, exactly like that. Space vector PWM can also be realized using the same carrier based approach like Sine PWM, and that made life a lot easier, because then we do not require any calculation, any sector identification or switching sequence design, etc. So, we can say that after this carrier based implementation of space vector PWM, we have made the space vector PWM an extension of the Sine PWM. Okay. Now, in order to realize this space vector PWM through carriers, we first observe the Sine PWM now in details. So, what happens in Sine PWM? So, here on this diagram we are showing the Sine PWM, where you can see the high frequency carrier here and 3 sine waves, 3 modulating sine waves balanced, that corresponds to VA, VB and VC. And then we also have shown the pole voltages VAO, VBO and VCO, which are fluctuating between 0 and 600 volt, the DC bus being 600 volts. Now, let us zoom into this portion of the waveform. Let us zoom in here and show it in the next screen. So, this is the zoomed version. Now, let us try to see the pattern of switching. Let us try to see the pattern of switching in this zoomed view. Let us concentrate here. Let us concentrate first in the first carrier, that is we are first seeing here. How do you see the pattern of switching? The carrier is here, and we are following the logic that if the modulating or the reference wave is more than the triangular wave, then we make the switch upper switch on, so that we get the full DC bus voltage. When the modulating wave is less than the triangular wave, then the lower switch is turned on and we get 0 voltage. So, the modulating waveform for A phase is this pink waveform here, the modulating waveform for B phase is the green one here, and that of the blue one here is the C phase. So, you see here that VAO is high up to this point, and then it goes low, because the modulating waveform is smaller than the carrier in this area. So, therefore, we have got a notch here going to 0. The rest of the time VAO is high. Similarly, VBO is high up to the point here, VBO is high, and then it goes low during this region as shown here, and then again it goes high like this. And VCO, you can see that it is low throughout this period and is high for the rest of the period. You can follow the pattern throughout. Now, then what is the pattern of switching? What is the pattern of switching? If you observe the first region here, we see that all three phases are 1. So, therefore, the first switching state is 1 1 1. After that, C phase goes to 0, while A and B phase are 1. So, we have a switching state 1 1 0. Afterwards, in this area we have B and C phases going to 0, whereas A phase is 1. So, we should have a switching state 1 0 0, and then here we have A phase, B phase and C phase, all three going to 0. So, therefore, we have 0 0 0 here. Okay. After this, A phase goes up while B and C phases are still down. So, therefore, we should have 1 0 0, and then we have a 1 1 0 here, that is here 1 1 0, and then you have a 1 1 1 where all three phases have gone to 1, that is 1 1 1, and so on in sector 1. So, it will again repeat for the next carrier and subsequently the other carriers. So, we see that in Sine PWM also, we have a switching sequence which is similar to that of space vector PWM. Okay. You see that this actually is in sector 1. Okay. The switching is happening in sector 1, and you see if you observe the switching sequence. So, we have started from 1 1 1 and then gone to 1 1 0, 1 0 0 and 0 0 0, and then again going back 1 0 0, 1 1 0 and then 1 1 1. So, basically we are switching in sector 1 here, and the switching sequence of going from, so there is only one switch which is changing at each switching change, only one phase is changing its state, other two are remaining constant. So, the switching sequence here is very similar to the switching sequence in space vector PWM. You can take any other sector. For example, we can take sector 2. Sector 2 somewhere is, for example, here, and you can again confirm that the switching sequence here in sector 2 in Sine PWM is very similar to the switching sequence of space vector PWM in sector 2. So, we see that there is a substantial similarity between how the switching sequence progresses in Sine PWM as well as in space vector PWM. Let us zoom in further into one carrier. So, which means that let us zoom in further into one carrier inside this carrier alone. Then there, so this is that carrier, this is the carrier there, and you have the three modulating waveforms A phase, B phase and C phase here. So, the A phase waveform and the C phase waveforms are positioned in sine PWM are positioned in such a way that it is not always that T01 and T07, that is the first and the last 0 vectors in a cycle, they are always equal. It is not the case in sine PWM. You can easily see that, because suppose in sine PWM A phase is reaching the top, which means it is close to 1. At that point in a balanced system, B and C phases are not at their negative maximum. So that the 0 vectors, that is the 1 1 1 and the 0 0 0, these two vectors in the switching cycle will not be equal. Okay. So, this unequalness of the two 0 vectors is what makes the difference between sine PWM and space vector PWM. In space vector PWM, the starting and the ending vectors, which are the 0 vectors, are always made equal, whereas in sine PWM they are not necessarily equal. Most of the time they are unequal. So, this is what you have seen. So, if sine PWM T01 time period and T07 time period are not always equal. Okay. So, this T01 by, so we have divided into two sub cycles, T01 by 2 and here also T07 by 2. So, this T01 by 2 and T07 by 2, these two lengths are not necessarily equal in sine PWM, and that is what makes it different from space vector PWM.